Yeah, thanks so much. Thanks so much for the invitation, and thank you all for coming. Um, so I'm going to, talk today about some work um, that I've done sort of at the intersection of stochastic geometry and the theory of random tessellations and sort of machine learning applications, specifically on this algorithm, class of algorithms called random forests. And this is joint work for the most part with collaborator Noctran. Okay, so the sort of problem setting for this talk is that of prediction. So this is where we're given sort of n example input and output pairs, and we want to obtain some estimator that will predict an output from some new input x. And there's of course many different algorithms and ways to obtain such an estimator. Random forests are a really popular class of algorithms for this task. And although they have been neural networks are sort of have sort of taken over in a lot of applications, including sort of like image processing and stuff. Random forests are still quite widely used and do achieve sort of state-of-the-art empirical performance for many tasks, in particular on tabular data. And the structure of these algorithms is that they are ensembles of randomized decision trees. So next, oops. So randomized decision trees are estimators that are obtained in the following way. So we recursively split the data along a random feature or dimension of the input, sort of like this animation shows. And this induces a hierarchical axis-aligned partition of the input space and simultaneously this random binary decision tree. And a random tree estimator takes some new input x, and the output is the average of the outputs corresponding to the inputs from this training data in the same cell as your new input x. And this is in particular in the regression setting. In the classification setting, you would take like a majority vote amongst the neighbors in the same cell or the same leaf as you. Oh, yeah. For a new input x, you look at these sort of your neighbors in the same cell to make the prediction. Now, a random forest, as I said, is an ensemble of randomized decision trees. And so what this means is that a random forest makes a prediction by averaging the predictions of MIID tree estimators. So this a random forest estimator is this random piecewise constant function that's constant over the cells of the partition induced by superimposing the partitions induced by each tree in the forest. The original random forest algorithm was developed sort of over by a few different authors sort of in the late 90s, but really popularized by Bryman in 2001 in a paper titled Random Forests. And in his original algorithm, the way the splits are generated to make this partition, while they are random, they are also highly dependent on the data. So in particular, when you want to make a split, you choose a random subset of the features or dimensions of your input. And then among all possible splits, you choose the split that minimizes the variance of the outputs from the training data in the resulting cells generated by that split. And this sort of data adaptivity is what leads to such great performance in practice, but also makes the algorithm very difficult to analyze. And there's still sort of a lack of theoretical guarantees and sort of complete theoretical understanding for the performance of this algorithm. And sort of historically, what many authors did was try to study simplified versions of this algorithm to better understand it. And this led to sort of this class of random forest algorithms called purely random forest variance, where the splits and the partition is generated independently of the data, which makes it much more amenable to analysis. One particular class of purely random forests that I want to focus on is generated from what's called the mandrian process. This is a stochastic process on the space of partitions that recursively builds this axis-aligned hierarchical partition in sort of an axis-aligned box in RD. So it's a well-defined process for any dimension D. It was introduced by Roy and Tay in 2008. And it was named after the painter because the resulting partitions that you get from this process are sort of reminiscent of his paintings. And so that's why this on the left is sort of a two-dimensional mandrian process that's sort of been colored in to look like one of his paintings. But there you also have a picture of a three-dimensional one because, as I said, they're well-defined in any dimension D. So how do these processes work? So I just want to quickly go through their construction. So we fix sort of an axis-aligned box in RD. And we also are going to fix a lifetime parameter. We want to think of this parameter really as a complexity parameter of the partition and of the sort of resulting estimators that we're going to construct from the partition. And we first start an exponential clock. And the parameter of this clock is going to be the sum of the widths of our box in each dimension. When this clock rings, if we've already passed the lifetime, then we're going to stop the process. Otherwise, we're going to sample a split by choosing a dimension randomly with probabilities proportional to the widths of the box in each dimension. And then conditioned on choosing dimension J, we're going to cut uniformly along the interval defining the box in that dimension. We then recurse independently on each subrectangle with lifetime given by the original lifetime minus the time that's already passed. So the next few cuts might look like this. And the lifetime is the total amount of time that you run this process. So the larger the lifetime is, the more complex that your partition is going to be. Shorter the lifetime, so the less complex it will be. So this is a hierarchical random partition of your space, which induces a random decision tree. So you can build random forests using this mandrian process. And in fact, given this construction and all of the exponential random variables and independence, this is actually a Markov process on the space of partitions. Which makes this process really amenable to sort of online algorithms where you're receiving more data over time and you want to update your estimator efficiently. So that was sort of one motivation for its initial introduction. Mandrian random forests also achieve comparable empirical performance for some to sort of the original random forest for some tasks. But of course, they really do not perform well in the presence of irrelevant features. So when the prediction depends, only on a subset of the dimensions or features of your data, and there are features that really have no influence on that prediction, the data adaptivity of random forests, adapts to this. It's going to cut more along the relevant features and less along these irrelevant features. But these Mondrian process is totally agnostic to that. And so that's why it really doesn't perform as well in those settings. But there's something really appealing still about this class of random forests beyond sort of the computational reasons and their amenability to online algorithms. From a theoretical perspective, it was the first class of random forests for which minimax optimal convergence rates were proved under non-parametric assumptions in arbitrary dimension. So I'll sort of mention again later more about minimax optimal rates, but just in some sense, in sort of this minimax setting, this among all sort of data agnostic or purely random forest variants, this partitioning process is somehow optimal in giving you the best possible convergence rates, minimax convergence rates. Yeah. Are there any questions before I move on? So there's a sort of remaining limitation, there's a limitation to Mondrian random forest and Bryman's sort of original random forest algorithm, which is that every time you make a split, you only use one feature or dimension of the input. And so these are just some sort of toy classification examples, just to try to give some intuition about how if you are if you're restricted to these sort of axis aligned splits, you are restricted to having these sort of stepwise decision boundaries. And for sort of data sets that might look like this, you might really need to run the process for a long time and potentially overfit to your data to get a good decision boundary. But if you had access to sort of oblique splits that use linear combinations of the features, you intuitively you could see how you might sort of do a better job and more efficiently split up your data. And indeed, there have been, there are many random forest variants that use oblique splits or linear combinations of the features to split the data that have been proposed in the literature. And they all, show improved empirical performance in a number of experiments over axis-aligned versions. However, there's even sort of more lack of a theoretical analysis of these variants. There's also increased computational costs and a lack of sort of amenability to online algorithms for most of these variants. And so a natural question is, since there are all these nice properties about the Mondrian process, is there specifically a generalization of this partitioning scheme with oblique splits? And the answer is really is yes, in this very exciting way, because the Mondrian process is actually a very special case of something called the stable underiteration process in stochastic geometry. This is also sort of a stochastic process that generates hierarchical partitions of our D. And it was introduced in the stochastic geometry literature back in, even earlier, back in 2003 by Nagel and Weiss. And their motivation was for modeling crack patterns in materials. And this is a very general class because it's actually indexed by what we'll call directional distributions on the unit sphere. And so these are, so basically for any probability measure on the unit sphere whose support contains D linearly independent unit vectors, there is a corresponding STIT process. So that condition on these probability measures just ensures that all the cells are going to be bounded. But other than that, for any distribution on the unit sphere satisfying that condition, you have a corresponding STIT process, and the construction is very similar to what I described for the Mondrian process. You have a lifetime parameter, and you assign the cells exponential clocks. When the clocks ring, you make a split. The difference is, like the parameter of the exponential clock depends on the directional distribution, and then when you make a split, you choose a direction by choosing a direction from this directional distribution weighted by the widths of the cell in each direction. But then once you have a direction, you cut uniformly along the width of the cell in that direction, just as in the Mondrian process. So in particular, when this directional distribution is the uniform measure on the unit basis vectors, the discrete uniform measure on the unit basis vectors, you recover the Mondrian process construction. And this picture here is a sample of a STIT process where this directional distribution is the uniform distribution on the unit sphere. And you see you get sort of much more complicated cell geometries. So there was one paper that sort of saw the connection between the Mondrian process and this more general class of random partitions. And they did an empirical study with random forests that were generated by a uniform STIT process, which showed improved performance over Mondrian random forests. But of course, these general cell shapes, they introduce both computational and theoretical challenges. And I bolded theoretical here because what this is, what our work has done has so far focused on the theoretical challenges by bringing in, additional theory from stochastic geometry on random tessellations in order to sort of address those. So in particular, we focused on, proving bounds on the generalization error or risk of a Stitt force estimator, and tried to generalize the results that have been obtained for mandrian processes. And the key difficulty here is that this error is controlled by geometric properties of the cells of this partition. And for a mandrian process, the cells are all these axis-aligned boxes, and we actually know exactly the distribution of the cell of a given input. We have this sort of random box whose width in each dimension is the sum of two exponential random variables, and they're all the widths are all independent. So you have very direct access basically to some geometric properties of the cells. But of course, with these more general Stitt processes, you have these much more complex random polytopes. And so it becomes, the theory that was developed for the mandrian process specifically is not easily generalized. So what our work did is really try to bring in some more powerful tools from the theory of random tessellations in order to understand these random forests. So before I actually state any of the results, I would like to sort of take us into a little bit more into stochastic geometry land, and I'd like to sort of give you a brief overview of what sort of viewpoint we brought in and what sort of tools we use to generalize or to study the error of these random forests. So the first thing is that, so I described this Stitt process construction on a compact window, and the fact that there's a generalization of that construction for any directional distribution on sort of a fixed compact window. And one of the first results that Nagle and Weiss proved about this stationary Stitt process construction is that it satisfies this consistency property, which means that if you run that process on a large compact window W2, and you intersect it with a smaller window, then the partition on that smaller window has the same distribution as if you had just run the process on that smaller window. And this consistency property allows you to define a Stitt tessellation on all of RD. And this is like infinite Stitt tessellation with an infinite number of cells. And it's also a stationary random tessellation, meaning its distribution is invariant under translations in RD. And this infinite Stitt tessellation has the property that if you intersect it with any compact window, you recover in distribution a partition of that compact window that would be induced by that Markov process. This infinite tessellation also satisfies what's called the stable underiteration property, which is where it gets its name from. And so the iteration of a random tessellation is where you subdivide each cell of the tessellation by an independent copy of the tessellation intersected with that cell, like this picture kind of shows. And if a partition is stable under iteration, it means that if you iterate the tessellation n times and then scale all of the boundaries by n, you recover in distribution the original random tessellation. And this is, so stable under iteration tessellations are all tessellations that have this property for any n. And in particular, an important consequence of this property is that these Stitt tessellations have the scaling property, which means that for any lifetime lambda, the stit tessellation with lifetime lambda scaled, and if you scale all the boundaries by lambda, you recover in distribution a stit tessellation with lifetime 1. So stit tessellations are just one sort of specific class of stationary random tessellations in stochastic geometry. And there are sort of two important random polytopes that we associate to general stationary random tessellations. So far, I've sort of been thinking about, we've been thinking about random tessellations as the union of the boundaries of the cells. Like to define that stable underiteration property, we're really talking about the union of the boundaries of the union of the hyperplane splits that we're making. But you can also look at the union of the cells of this process that are generated by all of these splits. And these form a stationary point process on the space of compact convex polytopes. So if you're familiar, with point processes, maybe you're familiar with point processes on the real line, or maybe even in RD. In stochastic geometry, we study point processes on much more general spaces, and specifically study point processes on those spaces of closed sets in RD. So one way of thinking of a random tessellation, or sometimes called a random mosaic, is just a point process on the space of compact convex polytopes that tessellate your space. So as I said, there are sort of two random polytopes important random polytopes we associate with these processes. One is the zero cell, which is just the unique cell that contains the origin. And by stationarity, this has the same distribution as the cell that contains any fixed location x in RD, translated so that x is at the origin. Another important random polytope is called the typical cell. And this is sort of an appropriately centered random polytope, such that if you want to compute the expected value of the number of cells in your infinite tessellation that have some property, this is equal to this expression that just depends on a single random polytope that we call the typical cell. So there are a few different ways to think of this typical cell. Like, very coarsely, you can sort of think of it as like a uniform random cell of the tessellation, which is not a precise definition because you have an infinite number of cells, and so the uniform distribution isn't well defined on that. But you can think about taking a really large ball in RD, and looking at all the cells that intersect that ball, and uniformly at random choosing a cell from that finite collection. And then the distribution of that cell as the ball grows to infinity approaches the distribution of the typical cell. You can also think about it like if you assign to each cell, if you're a little bit more familiar with point process theory at all, you can look at the centers of all of the cells, which form this point process in RD. And this typical cell is the distribution of the zero cell of the partition conditioned on one of those centers being at the origin. So that's another way to think of it. But this particular formula is very powerful and very useful. And in particular, there's something that will come up very soon when we go back to studying these stit random forests, is that the variance of a stit random forest is controlled by the expected number of cells, or in this partition of this compact window where your data is contained. And so we can sort of either think of that as like how many cells have you generated in this compact window, or as how many cells in this infinite tessellation intersect this compact window. And the expected value of that, using that formula on the previous slide, as well as a couple other things. So we use something called Steiner's formula, as well as the scaling property that I mentioned earlier. We get this polynomial in lambda, where the coefficients are all just geometric properties of this typical cell. And the typical cell here being the typical cell of the SIT tessellation with lifetime 1. So we use the scaling property to sort of pull out the lifetime lambda. And the coefficients all just depend on the typical cell of a SIT tessellation with lifetime 1. So that just depends on the directional distribution, not the lifetime. And this geometric property in the numerator, these are like mixed volumes of the typical cell. But the important thing here is that we're able to sort of discern what the order of this variance is with respect to the lifetime. I just want to pause there for a second in case there are any questions. Okay. So there's one more thing I want to tell you about before I get to our results, something that will show up in our statements. And that is this another parameter of these stationary random stationary STIT tessellations. And it's called an associated zonoid. So this is a now deterministic convex body whose support function is given by this integral that depends on the directional distribution and the lifetime. So zonoids are sort of a particular class of convex bodies that have a support function given by an integral of this form. So for any zonoid, there corresponds a STIT tessellation. And this parameter shows up when computing sort of statistics of the cells of these random tessellations. And you can, just for some examples for intuition, so for the mandrian, this associated zonoid is an L infinity ball. That's sort of the shape of all the cells, so that probably makes sense. For the uniform STIT, it's an L2 ball. And there's this other really interesting fact, which is, so here, so first, this is just sort of a simple, in the sort of weighted mandrian setting, a sort of relationship, what the relationship might be between the associated zonoid and a realization of the associated STIT tessellation. And a really, I think, beautiful fact is that the support function of the associated zonoid in a given direction V is actually the intensity of the Poisson point process that you get by intersecting the random tessellation with the line spanned with the span of that unit direction. So so the first fact there is that actually if you intersect the STIT tessellation with a line, you get a Poisson point process, and the intensity of that Poisson point process is twice the support function of the associated zonoid in that direction. Okay, so are there any questions before I kind of return to our results?
I guess one question I have is how sensitive are these beautiful properties to the choice of a lifetime distribution? So if you weren't to use an exponential distribution, I'd assume the formula on the previous slide would not hold or be.
So so the lifetime is a fixed parameter.
Oh, sorry, the clock distribution.
Oh, so the clock distribution is determined by it's determined by the directional distribution and it's determined by the directional distribution actually. So it's so in general, so you choose a direction by choosing a direction for directional distribution weighted by the widths in each of the cell in each direction. The parameter of the clock is actually like the sort of the total mass of that integral. If that makes sense. So the weight is actually the integral of the width of the cell with respect to directional distribution. And then you sample the direction from sort of the yeah, does that make sense? Like, so you have this like measure of the cell, the directional distribution weighted by the width. You normalize that to get a probability distribution. That normalization constant is the parameter of your clock.
I see. Okay, I might ask about this again at the end, but thanks.
Okay, yeah. Please do. Yeah, sorry. But yeah, all of these properties are true for sort of any directional distribution that satisfies that property I said, that contains the linearly independent unit vectors in its support, which ensures that you have all these bounded cells, and yeah, that allows you to sort of define the typical cell and all of these things, and so that they're all of the cells are compact convex polytopes. Okay, great. So next I want to return back to our application. So we want to study the risk or generalization error of these stit random forests, which are ensembles of stit random trees generated by these stit processes. So to set up the result, we're going to assume we're given, n IID samples of some random pair x, y. And we're going to assume this that all of our inputs are contained in the unit ball in RD. And then y is some unknown function f of x plus some noise. F hat is then going to denote our stit forest estimator, which is obtained by averaging m stit random trees, all with the same lifetime lambda and directional distribution phi. So our first result makes the assumption that f, our sort of unknown function, is Lipschitz. And in this case, we have the following upper bound on our generalization error or risk of our estimator, which is the expected value of the squared difference of our estimator minus true function applied at our random input. So the standard approach to obtaining an upper bound on this risk is to separate it into a bias and a variance, or approximation error plus estimation error. So this first term in the sum comes from an upper bound on the bias, or basically the error you get from the fact that we're really only, our model class is just these random piecewise constant functions. So what's the error between sort of the best possible thing you could choose from that class and our true function? It turns out this is upper bounded by the second moment of the diameter of the zero cell. And this is the zero cell of the, second moment of the zero cell. And so using that scaling property to pull out the lifetime, we see that the order of the bias is 1 over the lifetime squared. And the constant is the expected diameter squared of the zero cell of the stit tessellation with lifetime 1. So that constant just depends on the directional distribution. And then the variance comes from, as I said before, the variance can be controlled by the expected number of cells in the partition that's generated by a stit random tree. And so using that formula, this is sort of a simplified version of the formula I showed a few slides ago. And the simplification comes from the fact that we're now just assuming the window is a unit ball. And those constants, depending on the typical cell, end up reducing to these intrinsic volumes of the associated zonoid of the stit tessellation with lifetime 1. So the variance is just this polynomial in the lifetime, and the coefficients are just depend on this. So this deterministic convex body associated zonoid. So we can then sort of optimize this complexity parameter, the lifetime parameter. And if we let it scale like n to the 1 over d plus 2, as n, the amount of data that we have, grows, this upper bound gives us a rate of convergence for the risk that decays like n to the negative 2 over d plus 2. And this is actually the minimax optimal rate for the class of Lipschitz functions, which means that if you were to put, like this is sort of the best rate you could hope for in the worst case over this function class. So if you were to put a soup over all Lipschitz functions in front of this risk, in front of this, this error, there's a lower bound on that decays like n to the negative 2 over d plus 2. So in sort of the worst case over this function class, you can't improve this rate without any additional assumptions. So we call that all to say that basically for any directional distribution, STIT random forests are minimax optimal. Are there any questions about the statement? Okay, so there's a couple things I want to observe about this result. The first is that I haven't done anything about M here, right? So this upper bound holds just for a single STIT random tree, and the minimax optimal rate is obtained just with a single STIT random tree, which is surprising because in practice, when you average many trees to obtain a prediction, you get better performance. So actually, to address that point, we have a second result that makes some additional assumptions on our underlying function. So if we assume f is C2, then if we also make some additional assumptions about the input random variable x, we are able to obtain an improved rate of convergence on the risk by optimally tuning the lifetime and ensuring that M is large enough with n as n grows. Now, to obtain this rate, we do need to sort of condition that the input is a little bit away from the boundary to avoid these sort of edge effects. You can still get a rate without this conditioning. It's just it's not the minimax optimal one. But if you condition on the input being away from the boundary, you obtain this improved rate, which is the minimax optimal rate for C2 functions, which is only obtained if you have enough trees in your forest. Now, but the second thing I want to mention about both of these results is that actually, before I say that, sorry, I wanted to reiterate that both of these results hold for any fixed directional distribution. So the rates themselves, right? The rates themselves don't depend on the directional distribution. But as is clear from the full upper bound here, the constants definitely do depend on the directional distribution. And in fact, could get sort of arbitrarily bad depending on your directional distribution. Like the diameter of the cirrus cell could get very large if you don't have much weight in of your directional, like if you're not cutting up a certain direction very much. If you're weighted on sort of if the support of your directional distribution is not, we ensure that the cells are bounded by having support on d-linearly independent unit vectors. But if it's concentrated around a great subsphere of the unit sphere, then you could get, have a very large diameter of your zero cell. So I just want to sort of point that out, that for a fixed directional distribution, these rates hold, but you definitely have these directional distribution dependent constants in there. And then the last thing I want to say that will lead into the last part of the talk is that both of these rates suffer from the well-known sort of curse of dimensionality. So the dimension, the ambient dimension D of the input shows up in these rates. And when D is very large, these rates are both very slow. And this is just a product of the fact that we have only, the only assumption we've made about our underlying function is that it's Lipschitz or C2. So, we can't do better than these rates for these very general function classes. But, something we really wanted to understand was, can we get improved rates in higher dimensions by making making additional assumptions on the function, and maybe hopefully see actually some dependence on the directional distribution, and maybe show sort of an advantage of using these oblique splits, because using oblique splits gets you improved rates for some functions. So as I said, if we want to improve better rates, we need to make some additional assumptions. One sort of simple thing we can do, which plays very well with these random tessellations and gives us sort of an immediate improved set of rates, is to assume that our input is contained in a lower dimensional subspace of RD. So if this is the case, remember I mentioned that if you intersect a SIT tessellation with a line, you get a Poisson point process. This is a one-dimensional version of a more general property of these SIT tessellations, which is that if you intersect the tessellation with a general lower dimensional subspace, the partition induced on that subspace is again a SIT tessellation, and it's just the associated zonoid of that SIT tessellation is the projection of the associated zonoid in of the SIT tessellation in the ambient space onto that subspace. And so you can just sort of very immediately write down an upper bound when you make this assumption, where the bias then now just depends on the diameter of the zero cell intersected with the subspace, because you're really just looking at the diameter of the data of the input data in that cell. And then the variance is the same as before, but now the associated zonoid is this S-dimensional convex body. And so all of the intrinsic volumes above S are zero. Like the d-dimensional volume of this S-dimensional convex body is zero. And so this polynomial is now just on the order of lambda to the S as opposed to lambda to the D. So immediately we can get rates that are min-max optimal for functions on RS, just because now we basically have just the order for the variance and the bias that are needed to, if you tune lambda and m correctly, you get the same rates as I showed, but now just that instead of the rates depending on D, they depend on S. But of course, this is a very strong assumption about the input, and still we're not seeing a dependence on the directional distribution. I mean, again, the constants here depend on directional distribution, potentially even more heavily, but the rate still, you get an automatically improved rate for any directional distribution. A much weaker assumption we can make is, rather than the input being low dimensional, we can assume that our function only depends on a low dimensional subspace of the input. So f, sort of our unknown function, is actually given by some function g of s one-dimensional projections of our input. And we're going to call this low dimensional subspace that our function depends on the relevant feature subspace. And these sort of images just kind of are just trying to give a bit of an idea of why these two kind of scenarios are different and why the second one is a bit more difficult. So in the first picture is sort of the case where all of your data lies on this low dimensional subspace. And so, yeah, you see that sort of the ambient partition, whatever it is going to give you a pretty good partition of that subspace. So the data points they're close together, are going to be partitioned and stay together. But if your input data still lies in sort of d-dimensional ambient space, but your function just depends on their projection to this subspace, the partition of that ambient space is going to have a lot more effect on how well, it's not going to have a lot more effect on how well those points are partitioned once they're projected to that subspace. So if you partition these like the d-dimensional inputs by this ambient d-dimensional partition, you see that you're going to, if you're not sort of adapting that partition to this subspace, you are going to be sort of dividing points that really should be close once they're, that really should be together once they're projected to the subspace. And you might be, clumping points together that are actually far apart in this projected subspace. So it is just a sort of a cartoon to give you an intuition about why the second case is more difficult. So, hopefully from that picture, you see that ideally what you want to do is you just want to split up that low-dimensional subspace, because then all the points that would be partitioned once projected by those things it's the same partition that's induced if you just partition orthogonally to that subspace. But of course, in practice, we don't know what that subspace is. If we did, we just project all the data to the subspace and partition that. But in practice, we don't know this. So the result that we obtained is sort of to model a situation where we are sort of as we gain more data, we are sort of learning we're sort of learning the relevant features along which we want to split. But first, we can sort of give ourselves, given this assumption on our true function that it's called a ridge function or multi-index model, where our function just depends on sort of the projection of the input to this subspace. We get this upper bound on our risk, where the bias now depends on the diameter of the projection of the zero cell onto the subspace. And the variance, you now have what shows up is the diameter of the projection of the associated zonoid onto the orthogonal subspace to the relevant feature subspace, right? Because remember, the wider the associated zonoid is in some direction, the more we're cutting there. So we want, when we don't want to cut along the orthogonal direction. So we want the projection of that associated zonoid on the orthogonal direction to be small. And that's sort of where that shows up here. So if this is small, then we're going to get sort of an improved dependence. And if this is sort of decaying to zero as lambda is growing, we'll sort of get improved rates intuitively. And yeah, again, a picture of sort of what I was saying verbally, the associated zonoid, you want it to sort, the ideal associated zonoid is this S-dimensional convex body that lies in S. But if we are thinking about a situation where we're sort of learning that as we get more data, we want the associated zonoid to sort of be approaching that S-dimensional convex body in S. And the closer we're getting to that, so the more we're cutting along that relevant feature subspace. So in order to prove sort of a precise kind of guarantee that gives kind of what we wanted to prove is, how well do we need to be approximating these relevant features? How good of a directional distribution do we need in order to get sort of the optimal rates for this function class? To do this, we actually restrict to a specific class of STIP processes that have discrete directional distributions. So to define this class, we're going to parameterize this class by matrices, M by D matrices with rank D less than or equal to M. So the rows of this matrix, the direction of the rows are going to be the directions of in our directional distribution. And then the norms divided by the sum of all the norms are going to be the weights in our directional distribution. And the reason that we sort of are going to define this specific class of directional distributions is that these STIP processes can be generated by first applying A to our data and then running a mandrian process. So we don't actually have to deal with the more complicated STIP process generation to get a partition of the data that was induced by these STIP processes. All we have to do is apply a transformation and then run a mandrian process. So from sort of a computational point of view, this is nicer. And it's also generally how oblique splits are obtained in different oblique random forest variants in the literature. You transform the data and then run an axis-aligned partition. And this induces sort of non-axis-aligned splits on your original data. So for this class of processes, what we proved is basically that if we do a good enough job of choosing this transformation, so we have two conditions. We have one, that the sum of the L2 norms of the projection onto the orthogonal subspace of the directions that we cut in basically decays like 1 over lambda. So again, we want to be cutting along S. We don't want to be cutting along the orthogonal subspace to S. So we want the projection of the directions which we're cutting onto that orthogonal subspace to be small. If they're small enough, and if we're also still controlling, how good the tessellation is in S. So if the S largest singular value of the projection of our matrix onto S is sort of bounded below, this ensures still that the diameter of the cell within S, the zero cell within S, is still not going to be growing. Then if G tilde is Lipschitz, we can tune this lifetime parameter to scale like n to the 1 over S plus 2, and we obtain an upper bound on the risk that decays like n to the negative S plus 2 as n grows, which is the minimax optimal rate for these S-dimensional ridge functions. So to reiterate and sort of clarify, this is sort of modeling a setting where, we're sort of, as given a certain amount of data, we're learning a good directional distribution. So now the directional distribution depends on n. It depends on the amount of data that we have. And as n grows, if we're able to sort of learn a good enough directional distribution, this class of STIP tessellations has the power to achieve minimax optimal rates for this class of ridge functions. Okay, I'm running a bit out of time, so just to give a quick idea, the reason we can attain these these conditions and this rate, because for this specific class of STIP processes, we have these sort of exact we have these upper bounds on the diameters that show up in that upper bound on the risk that I showed earlier. Okay, so I'm pretty much out of time, so I apologize for going a bit over, but just to summarize, we've proved minimax optimal rate for a large class of random forest estimators with general oblique split directions, and shown how they can achieve improved rates in high dimensional space. But there's really still tons of work to do here. I think SIT random forests are really theoretically amenable class of partitions, of random partitions, both to develop more refined random forest variants, but also to develop to use in other applications that use random partitions. So there's lots of interesting directions where I think these sort of tools in stochastic geometry could be useful So thank you so much, and please, happy to take any questions that you have.
Thanks so much, Eliza. Great talk. Yeah, and welcome any questions from the audience. If not, I have one. In your opinion, what is kind of next on the mathematical side? So are there like barriers in understanding of stochastic geometry that need to be crossed in order to say say stronger things about more general models? Or
Yeah, great question. So I think there's still a lot. Yeah, there's I think a lot more that sort of existing theory can say. But I think the main direction I'm interested in, and I think would help understand more complex machine learning models that use random partitioning schemes, is to further develop the theory of non-stationary random tessellations. As I put a bullet point here. So I think stationarity is really a limitation for these models in modeling other things that are done, like machine learning models that I use in practice, but also for just developing maybe more powerful schemes that can capture more complex structure in the data. So you can you can imagine that like the important features are not sort of uniform in space. So like you might in one area of sort of input space, like the relevant features are not like sort of uniform in a given subspace across and so you want sort of maybe more local dependence, like a directional distribution that depends on where you are in space. And that is much less developed in the stochastic geometry literature. There's a few papers that discuss non-stationary random tessellations, but I think the key there is to find a specific like parametric class of stationary random tessellations that captures maybe some sort of known data structure, or just like some parametric class that balances expressivity with computational, like ability to actually compute an optimal set of parameters or something from that class. And so this is I think a really interesting future direction. But the key there is kind of what characteristics of non-stationarity do we want? What kind of key non-stationariness like is the best for natural data sets? That's sort of a difficult question, I think.
Right. Got it. Thanks. Okay. Any further questions? And if not, well, thanks so much again, Eliza, and have a great week to everyone, and see you next time.
Yeah. Thank you all so much for coming. If you have any other questions, feel free to email me or anything. Thanks so much.
Take care.